On example number 2, I'd like you to actually go ahead and see if you can try to work through this problem on your own. This is a problem that we actually saw in the last section. At Anytown College, 100 students were randomly surveyed. It was found that out of these 100, 55 own a bike, 30 own a car, and 10 students own both. And you might recall that we set up this table of information. Here I've just asked a couple different questions about it, and I'd like you to try to think about how you would interpret these sentences. Notice that's an English question, not as much a math question. But start by going ahead and seeing if you can create some probability notation for each one of the different parts that we have here, and see then if you can go ahead and actually try to calculate the associated probability. Hit pause right now, give that a shot, and then of course when you hit unpause, you'll see me work through the solutions. All right, let's see what we have here. I want to know what is the probability that a student owns a bicycle given that he or she owns a car. So bicycle given they own a car. Again here I'll notice that I have numbers in my table as opposed like whole number counts as opposed to percentages. So I'm going to say that I want to grab the number of people in B and C divided by the number of people in the given group, which is C. That's the way I calculate a conditional probability every single time. All right, so let's see. The number of people that are in B and C, that should be 10. The number of people that are in just C overall is 30. So as a percentage, this would just be 0.3333. Boom, there we go. Okay, let's take a look at part B. Suppose a student does not have a bicycle. What is the probability that he or she has a car? Notice that the word given here didn't occur at all. However, if I think about what the sentence is really saying, I'm told that I already know the student does not have a bicycle. That's given to me. What I want to know is, does the person have a car? So again, I'm just going to calculate the number of people that are in both of those groups at the same time over the number of people in the overlap. Or sorry, in the given group, excuse me. So if I look at the numerator here, I can see that the number of people that are in group C and are not bike owners, that's 20. The number of people that are just not bike owners is 45. So I have 20 out of 45. If I was to go ahead and write that down as decimal, I get 0.4444. Okay, great. Let's see. Part C. What are the chances that a student doesn't own a bike and doesn't own a car? All right, well, let's see. Doesn't own a bike would look like this, and doesn't own a car. Notice nothing here is given. I don't know if this person owns a bike or a car. I'm not saying that I'm already going to go look at people that meet one of these two descriptions. I'm kind of curious about both descriptions. This is an and question. And remember that I don't actually have any fancy formulas to compute an and at this point because I didn't need a fancy formula. Can't I automatically find all of the people out of the total 100 individuals that meet both descriptions at the same time? Where are the people in the table that do not own bikes and do not own cars? Well, they're right there. There's 25 of them. Notice no fancy formula needed here because I wasn't dealing with the conditional probability. So, boom, there I go, 25%. So this is hopefully a good example that can allow you to see that I do have to be a little bit careful. Chances are, if you messed up on a question here, it might have been part C because you might have been trying to force a given or a conditional probability to occur here. And so you just got to be aware that hey, these sorts of questions can be jumbled together. What will be more interesting is that in the next couple videos, we're going to see how we might be able to compute probabilities that involve and when the meaning of and changes. You can see here that and just kind of meant that I want both of these things to happen at the same time. But sometimes in English we use the word and to communicate a sequence of events. Like I want thing A to happen and then I want B to happen, like a progression through time. And that sort of a probability question is a little bit different and requires a new rule that we'll call the multiplication law of probability.